So today's lesson is going to be regarding chapter 4, which is all about light and the electronic structure. So I want to start off this lesson with a question. What do you think do infrared, UV, and X-rays have in common? So the answer is they are actually all examples of light that we can't see with the naked eye. When Albert Einstein was just a little kid, he actually asked a lot of questions regarding the nature of light. What is light? And light is basically an electromagnetic radiation. So typically when we hear the word radiation, we panic, right? Because we think it's a bad thing. But not all radiations are harmful. And you'll learn all about the electromagnetic radiation today in this lesson. So by definition, an electromagnetic radiation is the oscillating waves of electric and magnetic fields propagating through space at the speed of light. And speed of light in vacuum is equivalent to 300 million meters per second. That's fast, right? So it's 3 times 10 raised to the 8th power meters per second. So how fast is this speed of light? Well, if you do some calculations, light can travel around the globe 6 to 8 times per second. That's how fast it is. You can also look at it in terms of how fast or how long it will take for the sunlight coming from the sun to reach Earth. It will only take about 8 minutes. So that's how fast this light is in vacuum. So what does it mean when we say that an electromagnetic radiation contains oscillating waves of both electric and magnetic fields? Well, we can look at it in terms of a graph. So in this graph, we have both electric field and magnetic field. So the electric field is in red and the magnetic field is in blue. And as you can see here, this electric field in red is oscillating perpendicular to the oscillation of the magnetic field. And in physics, if you've taken intro to physics, maybe back in high school, you've probably heard of this term they call the right-hand rule. So the right-hand rule basically helps you identify the direction of the magnetic field relative to the electric field. So I'm basically holding my hand up with my thumbs pointing up, kind of like a like button. And so when the magnetic field is going in a counterclockwise direction, then the electric field is pointing upward direction, okay? And if the magnetic field is going in a clockwise direction, then the electric field is pointing down. So that's basically what the right-hand rule is. It tells you the relative direction of the magnetic field from the electric field. So now this electromagnetic radiation actually ranges from very low energy waves to extremely high energy waves. And so because it's a range from low to high energy, an electromagnetic radiation is actually a spectrum, an electromagnetic radiation spectrum. Kind of like autism. When you look at autism, there's high functioning autistic people, and there's also the low functioning autistic people. So it's a spectrum similar to electromagnetic radiation. Since light is an electromagnetic radiation, light must be a wave containing oscillating magnetic and electric fields traveling at the speed of light. So this is what light looks like. So we know that light is an electromagnetic radiation and that there are several different types of light. There's light that's high in energy and there's light that's low in energy. And so it's a spectrum. So what's shown here is the electromagnetic radiation spectrum. So this region over here, somewhere in the middle that looks like a rainbow, is known as the visible region of the spectrum. So this is the type of light that we can see. That's why they call it visible light. All the rest here, we can't see them with the naked eye, right? For example, we have radio waves, microwaves, infrared light, UV light, X-rays, and gamma rays. These are the type of light or radiation that we can't see with the naked eye. So how do we know that light is an example of a wave? So we know that light is a wave because it has wave-like properties or characteristics. And these properties are measurable. So what makes a wave a wave? Well, we have to look at the characteristics of a wave. What are these characteristics? So there are three that you need to know. The first one is amplitude. So a wave has an amplitude. It has a wavelength as well. And the third one is frequency. And these are the symbols of these characteristics. So amplitude has a symbol capital A. Wavelength has the symbol lambda, which is a Greek letter. And frequency has this symbol called nu, Nu, which is also a Greek letter. So the amplitude of light basically tells you how intense or bright that light is. So the higher the amplitude, the higher the intensity or brightness of that light. And so if you look at, let's say, 5 red lasers and you point all of them in one direction or in one spot, you'll notice that the brightness increases as well as the intensity. And so the reason is because of the amplitude. So you can combine these lasers together to form one bright light. But our focus here will be on the last two, wavelength and frequency. You only need to know the definition of amplitude and what it is. But wavelength is measured in meters or nanometers because it's a length. It's a wavelength. It's the length of a wave. Frequency, by definition, is the number of cycles per given time, and it's usually per second. And the unit is per second, 1/s, or inverse second. And 1 inverse second is actually equivalent to 1 hertz with the symbol Hz. Okay, so let's look at this graph shown here. So this is a graph of a wave. If you've taken pre-calculus or trigonometry in the past, this is what a sine wave looks like. Okay, so it's a graph of a wave mathematically. What amplitude is basically the height of this wave, right? So if the total height is from up here all the way to here, then the amplitude is half that total height. Okay, so that's amplitude. Wavelength, on the other hand, is measured in meters or nanometers, and it's the distance between two maximums. Okay, so this is the wavelength of that wave. And so the distance between here and here is actually equal to the distance between the two bottoms here. The two minima, as they call them. All right, so those two are equal. So that's the main difference between amplitude and wavelength. So what about frequency? What does frequency look like in terms of a graph? Well, so we can look at another graph of a wave shown here. And let's say this is the 1 second mark and this is the 2 second mark, right? So t equals 1 and we have t equals 2. And by definition, frequency is the number of cycles per time. So let's say that frequency is the number of cycles per second. Then we can look at the number of wave cycles per second, right? So in this one, we have many more cycles per second on the first second, right? The first 1 second compared to the next 1 second. So you have less number of cycles of waves here compared to the first second. And so in other words, you have lower frequency on the right compared to the one on the left. So we have higher frequency on the left because of the number of wave cycles per second, and lower frequency on the right because there's less number of cycles per second. So frequency and wavelength are actually mathematically related. So what that means is that if you know the frequency of a wave, you'll be able to calculate and determine the wavelength of that wave, and vice versa. So if you know the wavelength, you can calculate the frequency. So let's analyze this graph shown here. So again, by definition, a wavelength is basically the distance between two bottoms, right? The distance between two minimas or the distance between two maximas. So if you look at the wavelength over here where there's higher frequency, we can label this lambda 1, okay? Lambda 1, which is related to a higher frequency. And then we can compare it to the next wavelength, which is this one, labeled lambda 2. So as you can see here, lambda 2 has a longer length compared to lambda 1. So that means that lambda 2 is a longer wavelength than lambda 1. And look at how lambda 2 is related to the frequency and lambda 1 to its frequency. You can see then that the longer the wavelength, the lower the frequency, and vice versa. The shorter the wavelength, the greater the frequency, or the higher the frequency. So that's the relationship between frequency and wavelength. Frequency is inversely proportional to the wavelength. Okay? So again, what that means is that if one increases, the other one decreases, and vice versa. So to illustrate this concept regarding frequency and wavelength, we can look at this example shown here. So we have the visible region of the electromagnetic spectrum, where you have red light all the way to the blue light. So this is the wavelength here. So for the red light, it's about 750 nanometers. The wavelength of the green light is 535 nanometers. And then for blue light, it's 400 nanometers. And then we also have the frequency already shown here. So as you can see, the lower the frequency, the shorter the wavelength, the higher the frequency, right? So 750 versus 400, we have 400, which is the shorter wavelength, and it has higher frequency compared to the red light, which has basically frequency half of the blue light's frequency. This equation right here basically shows you the mathematical relationship between frequency and wavelength. So again, this is the symbol for frequency here, and this is wavelength. And lowercase c is the speed of light. And again, the speed of light is equivalent to 300 million meters per second, or 3.0 times 10 to the 8th power meters per second. And again, this is a symbol for wavelength. And so before you plug in any numbers for wavelength in this formula, make sure that you convert the wavelength to meters first. Okay, and then frequency is in inverse second. All right, so let's look at a few examples here. Calculate the frequency of red light with a wavelength of 720 nanometers. So how do we calculate the frequency of this red light? Well, you're given the wavelength, which is 720 nanometers. So all you have to do now is use the equation that you learned in the previous slide and apply it here. So this is the equation, and we can simply calculate the wavelength by plugging in the numbers, the values here. So we know the value of the speed of light. It's 3 times 10 to the 8th power. And we also know the wavelength, which is 720 nanometers. But remember that you can't just plug in 720 nanometers here. You have to convert nanometers to meters first. And the easiest way to do that is to just multiply this by the equivalence, the numerical equivalence of the prefix nano, which is times 10 to the negative 9th power. Right? So you can just plug that in here. So 720 times 10 to the negative 9th meter. Plug this into your calculator and you'll get 4.2 times 10 to the 14th inverse second. So that's the frequency of red light with that specific wavelength. All right, let's look at the second one here. Calculate the frequency of green light with a wavelength of 500 nanometers. So we can do the same thing. We can use the same equation shown here and plug in the numbers. So we have 3 times 10 to the 8th power for the speed of light divided by 500 times 10 to the negative 9th, because we're converting it from nanometers to meters. Plug this into your calculator and you get 6 times 10 to the 14th power inverse second. And the last question here, calculate the wavelength of blue light with frequency equal to 6.41 times 10 to the 14th hertz. All right, so now we have to calculate the wavelength and not the frequency. But we can use the same equation here, right? The same formula. Frequency is equivalent to the speed of light divided by wavelength, which is lambda. So we can use algebra here to isolate the wavelength. So we want wavelength by itself, so we're going to move it to the left-hand side of the equal sign, and then move frequency to the right-hand side of the equal sign. So to do that, we're going to multiply both sides by wavelength. And you can see that the wavelength will cancel out on the right-hand side of the equal sign. But we want wavelength by itself. Right now, it's lambda times wavelength times frequency equals the speed of light. So let's clean this up a little bit here. So now to isolate wavelength, we're going to divide both sides by frequency. So frequency will cancel out on the left. And now we have an equation for lambda, which is the wavelength. So we can plug in the numbers. The speed of light, again, is 3 times 10 to the 8th power divided by the given frequency here. And that gives us 4.68 times 10 to the negative 7 meters. Okay, so take note of the unit here. It's in meters because the seconds cancel each other out, and you're left with the unit meter. Some maybe on the test or online in the online homework, they might ask you for the wavelength in nanometers instead of meters. And so after solving for the wavelength, make sure to know what the unit is, whether it's in meters or nanometers. So if you get this, and it's asking for nanometers, then you have to convert this to nanometers by simply multiplying this by 10 to the 9th power, okay, or divide it by 10 to the negative 9 power. It doesn't matter, right? So this is equivalent to 468 nanometers. So you just learned that light is an electromagnetic radiation, and that there's a lot of different types of light. There's UV light, there's gamma rays, X-rays, and so on and so forth. And each type of light has energy, right? And that's why UV light can burn your skin, and X-rays can damage your bones and can cause cancer, and so on and so forth. That's because light contains energy. So light contains photons, and each one contains energy. And photon, by definition, is a massless particle or packet of energy. And Einstein is actually the one that did this, or proved this mathematically and experimentally. There's another physicist that did a lot of work, a lot of theoretical research regarding the nature of light and how that's related to energy. And his name was Max Planck. So Max Planck was able to introduce this new equation that relates energy and frequency. So the energy of light and frequency of light are both related via this mathematical equation. So E equals H times nu. Okay, so H is known as Max Planck's constant. And Planck's constant is equivalent to 6.626 times 10 to the negative 34th joule seconds. And energy here is measured in joules, capital J. And again, nu is the frequency. And this is usually in inverse second or hertz. And we can also use this equation shown here to basically relate wavelength, which is lambda, to the energy of that light. So in this case, lambda, the wavelength of light, is inversely proportional to energy. Whereas in this first equation here, the frequency is directly related to energy. So if the frequency of light increases, so does the energy of light, because you're multiplying frequency by Planck's constant. Whereas in this equation, as the wavelength of light increases, the energy of light decreases, because you're dividing this by the wavelength. So we have Planck's constant again. So E equals Planck's constant times the speed of light divided by the wavelength of light. So again, the wavelength has to be converted to meters first. So if you were given the wavelength in nanometers, you have to convert that to meters first before plugging it into this equation. All right, so let's look at some of these examples shown here. Again, you can pause this video if you want to try them out yourself. The first question here is calculate the wavelength and energy of a photon with this specific frequency. So you're given the frequency here and you have to calculate wavelength and energy. So we can use this equation shown here to calculate the energy. Okay, so we're given the frequency of light. We can solve the energy using this equation. So all we have to do is multiply the wavelength, the frequency by this constant, Planck's constant. So in that case, 6.626 times 10 to the negative 34th times the given frequency. And you can see that the unit seconds will cancel, and you're left with joules, which is the unit of energy. So multiply the two numbers and we get 4.97 times 10 to the negative 19 joules. All right, so to solve for wavelength, we can use the other equation that relates frequency and wavelength. So wavelength is equivalent to speed of light divided by wavelength, shown here. All right, so all you have to do now is plug in the numbers. We know the speed of light. It's 3 times 10 to the 8th power meters per second divided by wavelength. We also know the frequency. So all we have to do is rearrange this equation and isolate wavelength by itself. All right, so once you rearrange it, you get this equation for wavelength. Okay, so all you have to do now is plug in the numbers. We have the speed of light, which is 3 times 10 to the 8th power, divided by the frequency given here. And that gives us 4.00 times 10 to the negative 7 inverse second. All right, for the second question here, calculate the energy of a blue light with the frequency or with a wavelength of 400 nanometers. Okay, so we can't use this equation up here because we're not given the frequency. What you can do is you can convert this to frequency first if you like, and then plug it into this same equation. Or we can just use the combined equation, right, relating energy and wavelength. So in that case, energy is equivalent to hc over lambda. Okay, so Planck's constant times the speed of light divided by the wavelength. So Planck's constant times the speed of light divided by wavelength. So again, you can't just plug in the number. You have to convert this from nanometers to meters. And you can do that by simply adding times 10 to the negative 9 in this equation. So you can see the seconds will cancel, meters will cancel, and you're left with the unit joules, which is the unit that we want, a unit of energy. So we get 4.97 times 10 to the negative 19th power. Third question here, calculate the energy of a red light. And again, we're given the wavelength of light, 700 nanometers. So we can use the same exact formula here, or equation. So E equals hc over lambda, and plug in the value of Planck's constant and the speed of light, multiply them together, and then divide it by 700 times 10 to the negative 9th meters. And that gives us 2.84 times 10 to the negative 19 joule. So now, which color has the higher energy? Is it blue or the red light? Well, you can compare them using the numerical values that we just calculated. So this is for the red light, 2.84 versus the blue light, which is 4.97. So you can see that blue light has the higher energy compared to the red light. So when you look at the colors of the rainbow, you have red, orange, yellow, blue, green, violet, right? So Roy G. Biv. Violet is closer to the ultraviolet region of the spectrum, and it has higher energy because it can damage your skin, right? It can burn your skin, compared to red or infrared, because infrared is weak in energy. And so again, red and orange, those are the weaker energy, whereas the blue and violet are the higher energy if we're looking at the visible region of the spectrum. So if we look at the relationship between frequency and wavelength, you remember that the shorter the wavelength, the higher the frequency. And similarly, the longer the wavelength, the lower the frequency. And then we just learned in the previous slides that the higher the frequency, the higher the energy, because they are directly related. So the higher the energy, the higher frequency, and vice versa, which is the opposite for wavelength and energy. So now when you look at the wavelength, the shorter the wavelength, the higher the energy, and the longer the wavelength, the lower the energy. And to summarize all of that, the increase in wavelength basically results in the decrease in both energy and frequency. Or you can also reverse this statement. The decrease in wavelength results in the increase in both the energy and frequency. So now let's look at the relationship between color, line spectra, and the BOUR model of the atom. So different fireworks produce different colors. And the reason why is because these fireworks contain different types of metals that get burned in the process. So for example, if you have magnesium, that will produce white light. If you have copper, bluish green, sodium, yellow. And you also have these other metals here, like calcium, for example, produces orange, strontium produces bright orange, and so on and so forth. And all elements in the periodic table give off light, which is energy, when burned or exposed to electrical energy or other sources of energy. Heat, for example, is a source of energy. So when you burn a metal, it produces a specific color. So when you go to bars and restaurants, you'll see a bunch of neon lights, like the open sign, for example. When you go to New York City, Times Square, you see a lot of lights there. Those are neon lights as well. But what are these neon lights exactly? Well, they're basically glass tubes filled with noble gases. And noble gases are the elements in the periodic table on the far right-hand side. So you have helium, neon, argon, krypton, and xenon. So essentially, neon lights are examples of the cathode ray tubes that you learned in a previous chapter. So when you fill a glass tube with one of these gases and then expose them to electrical energy or electrical source, they light up. Okay, it's because the atoms, the noble gas atoms, are interacting with this energy, the electrical energy, and it basically converts it into light. And so again, as I mentioned earlier, neon lights are basically gas lamps, and these gas lamps or vapor lamps produce light by passing an electric current or electric energy through a tube filled with a noble gas. And this is very similar to the metals that I showed you earlier. When the metals get burned, they produce a specific energy, specific color of light or wavelength. And so like the metals, each gas produces a unique characteristic color. So this specific characteristic color that's produced or generated by the elements is actually a combination of different colors with different wavelengths. It could be a combination of blue, green, and red, or any of the other colors of the rainbow. So here's an image of white light that gets separated or diffracted into its individual colors. So when you pass a white light through a prism, a glass prism, the light gets separated into individual colors that you see in a rainbow. So here's an image of a sodium vapor lamp. So it's basically a lamp containing the element sodium in vapor state or gas state. So it's sort of similar to a neon light, except we have sodium instead of the noble gases. So when you expose this to an electrical source, the lamp lights up, right, because of the gases. So the sodium gas is interacting with that electrical energy and gets converted into light, yellow light. So to us, it looks like it's generating yellow light, but is it only one wavelength, or is it a combination of different wavelengths, different colors? So if we pass this yellow light through a prism, a glass prism, it'll actually diffract into other colors of light. So a sodium lamp, a sodium vapor lamp, generates three colors, a combination of orange, yellow, and yellow-green. So this yellow light that's produced by the sodium gas lamp basically separates further into distinct lines of color, and they call this spectral lines. And these are the lines that are contained in what they call emission line spectrum, or simply line spectrum. So shown here are different examples of emission line spectra. So we have the emission line spectrum of sodium, hydrogen, calcium, and mercury. So we looked at sodium earlier. So sodium produces yellow light, and when you pass that through a glass prism, it'll generate a spectral line containing yellow, orange, yellowish green, and looks like a tint of blue as well. Okay, when you do the same thing for a hydrogen lamp, for example, it will generate this combination of light. Okay, calcium will have many more lines or spectral line here, and mercury a different combination of wavelengths of light. So as you can see here, all these four elements have very unique combination of spectral lines, right? So the emission line spectrum for sodium is different from that of hydrogen, and hydrogen has different combination of spectral lines compared to calcium and mercury. And so because each element in the periodic table is unique, they each have a unique emission line spectrum. And so we can use this line spectrum to identify what kind of element we have in a given sample. So analyzing an unknown sample's line spectrum allows us to identify what kind of elements are present. So for instance, if we want to know if we want to know if there's lead or mercury in our drinking water, we can use this technique called atomic spectroscopy, which again is a technique that allows you to determine what kind of elements you have present in the sample. And it utilizes this concept of emission line spectra. So what exactly do these spectral lines mean? What do they exactly tell us? So there was this Danish physicist named Niels Bohr who came up with an explanation regarding this phenomenon that people observed regarding the atoms. So he explained it using his own model of the atom. So around this time in the 1900s, a lot of people jumped into the field after the publication of the atomic theory. J.J. Thomson came up with his own model of the atom. He called it the plum pudding model. And then Rutherford came up with his own model, the nuclear theory. And we also have Niels Bohr, who explained the spectral lines using his own model of the atom. So you're completely familiar with this. You have the nucleus in the middle. The nucleus contains protons and neutrons. Now Niels Bohr, he also included that the atom consists of energy levels, right, or orbits, but he used the term stationary states. Okay, these stationary states are basically orbits or energy levels. So you have energy level 1 or stationary state 1, energy level 2 or stationary state 2, 3, 4, so on and so forth. And in these stationary states, you have electrons. Okay, and these electrons revolve around the nucleus, kind of like the planets revolving around the sun, right? So this is very similar to the planetary model. So you have electrons orbiting the nucleus. So the orbits or energy levels closer to the nucleus are actually lower in energy. Okay, and so the energy levels or stationary states that are farther away from the center, farther away from the nucleus, okay, are higher in energy. Okay, so energy level 1, for example, or stationary state 1 is less in energy compared to energy level 2 or stationary state number 2. And you can also use the same argument when it comes to electrons. So the electrons, the energy of the electrons in level 1 is less than the energy of the electrons in level 2 or higher, and so on and so forth. So that's the basic idea regarding the electronic structure of the atom that Niels Bohr introduced around that time in the early 1900s. So these stationary states or energy levels shown here, they have very specific energy. And so the electrons that are orbiting the nucleus in a certain stationary state has a specific energy as well. And so one thing that you need to know here is that electrons can jump from one energy level to another, but they can only do so by either absorbing energy or releasing energy. Okay, so electrons can jump from one energy level to another by absorbing energy. Let's say if you want to move from energy level 1 to energy level 2, then they have to absorb energy. Or they can release energy to move from a higher energy level to a lower energy level. So they call this emission. Okay, so light has to be released or emitted in order to move to a lower energy level, and you have to absorb energy in order to move to a higher energy level. So here's a few more things that you need to know regarding Bohr's model of the atom. So the lowest energy level is known as the ground state, and any higher energy level beyond the ground state is known as the excited state. So whenever you feel excited, you usually have a lot of energy. And so the excited state has a higher energy than the ground state. And when an electron moves to a different energy level, that process is usually known as a transition. So when an electron moves from, let's say, energy level 1 or stationary state 1 to the fourth energy level, then that's a transition. Okay? And an electron has to absorb energy in order to get to a higher energy level. And when an electron moves to a lower energy level, let's say from E4 to E1, then that's known as an emission, because that electron has to emit extra energy in order to go back down to a lower energy level. So Niels Bohr essentially used this concept to explain the spectral lines that are observed from the elements. So the spectral lines come from electrons emitting or releasing energy in the form of light.